Good morning. Last week we started talking about bonding, and we're going to continue that discussion with some representations of molecules. Especially when we're talking about molecular formula, this is going to be really apparent. So typically we use a chemical formula, and that's how we show our bonding. And whether it's ionic or covalent, either way we can draw a chemical formula, though oftentimes molecular formulas will have multiple atoms. The amount of information, though, about the structure is varied depending on what model we use. And sometimes we can show more by showing different models and how we represent it. There's no exactly perfect model, but we can get pretty close to a representation of what's occurring. Any chemical formula is going to tell us what elements are in the compound. That's kind of given. So for example, this is C2H2O4. We know there's 2 carbons, 2 hydrogens, and 4 oxygens. So that gives us some information. We know we have carbon, hydrogen, and oxygen. This doesn't quite tell me everything, though, about the compound. And it also might not tell me the exact amount of each atom we have. I know that this is probably the exact amount. And I'll tell you why in a little bit. But this definitely tells you the ratio, and it tells you all the atoms that are present. So a compound is made up of 2 or more elements, of course. And they could be molecules, they could be ions. And we looked at that last time. This one we know is a molecular compound because it's all nonmetals. So we don't have any ionic bonding in this particular compound. And each element is represented by a letter symbol, but the number is not quite everything. So also note, just like always, and we'll see this throughout, we don't like to write ones in chemistry for some reason. So if there's only one atom, we won't show the one. But otherwise, in our subscripts, we'll show how many of each of those elements we have in that compound and those bondings. But we won't typically show the one, which is common. If there are multiple polyatomic groups, then we would put them in parentheses, and we'll look more at that in a couple of slides. So the first formula that I want to talk about is the empirical formula. All the empirical formula does is tell us the elements that are present and the ratio those elements are present. But it might not show the exact amount of elements present. So it's our lowest number ratio. It may describe the total amount, but it may not. So for example, I know that this one is likely not the empirical formula because we don't have the lowest number ratio. I can still divide all those subscripts by a number and still get a whole number. So that's why I said this is likely the exact amount of carbons, hydrogens, and oxygens. But an empirical formula doesn't necessarily show you the exact amount, it just shows you the lowest whole number ratio of each element to each other element in the molecule or compound. They don't tell us our order of attachment or shape that our atoms are attached in. And this will be really important if you decide to take organic chemistry. We'll see that really prevalent in organic chemistry, that the way that we put our atoms together in a molecule could change, especially when we're talking about carbon-containing molecules, because the more carbons we have, the more different ways you can attach it together and still have that same formula. So this doesn't really tell us anything other than the lowest whole number ratio of each atom, and it tells us which elements are actually there. So hydrogen's not shown, there's no hydrogen in the molecule. Oftentimes for ionic compounds, the empirical formula is what's shown. And that's because ionic compounds are an array of our ions that are attracted to each other. So typically ionic compounds, our empirical formula equals our regular formula. But for organic molecules or covalently bonded atoms, oftentimes our empirical formula does not equal our molecular formula. There's a couple of exceptions, of course. So what this empirical formula, CaCl2, tells me, for every one calcium ion, I have 2 chlorine ions. And we'll look at that in more detail in a little bit as well, and talk about why that is. But the empirical formula for the molecule compound oxalic acid, CHO2, might not tell us exactly how many carbons, hydrogens, and oxygens we have in a molecule, but what we do know is we have 1 carbon for every 1 hydrogen for every 2 oxygens in that molecule. So it tells us our lowest whole number ratio. But it might not actually tell us the total number of carbons, hydrogens, and oxygens. So it could be C2H2O4. It could be C22H22O44. It's still going to be a ratio of 1 to 1 to 2. And we don't know unless if we know more. So the empirical formula doesn't necessarily tell us the total amount of atoms. The actual formula is C2H2O4. But you wouldn't know that unless if we did more to find that out. And you do not need to memorize the actual molecular formula of oxalic acid. It's not necessary. So our molecular formulas describe the exact amount of atoms in your molecule. So it tells you all of the elements, and it tells you how many each of those elements are. It still doesn't describe our order of attachment or our shape. There's still more we might need to know about them, but it does tell us how many atoms are there. So for example, our molecular formula for oxalic acid is C2H2O4. It's not our lowest number ratio, but it is our formula. But it doesn't tell us how they're attached. You wouldn't know necessarily from looking at this formula that we have 2 carbon-oxygen double bonds, 2 alcohols, and 1 carbon-carbon single bond. I do because I'm a bit better at figuring out organic compounds than you are. And then later on, if you did have a compound that was C22H22O44, there is probably 1,000 ways you can put that together to where it would still be in agreement with that formula. So this doesn't tell us attachment, but it tells us a little bit more than our empirical. Our structural formula describes how the molecule is attached. So this is oxalic acid, and as you can see, this tells us a bit more. Now I see that I have 2 carbon-oxygen double bonds, 2 OH groups, and 1 carbon-carbon single bond. That's pretty straightforward looking at this. Bless you. Would you get this from this? You might not. But like I said, if you decide to take organic chemistry, you probably will. And when we talk about chapters 9 and 10, we might get a little bit into drawing this. So our structural formula tells us more. It tells us attachment and the order of attachment. It tells us that the carbons are each attached to 2 oxygens. It tells us the carbons are each attached to 1 other carbon. So it tells us a bit more. It's still not really necessarily showing shape, but when you do get to organic chemistry, we learn that we typically do draw shape into this to be more clear. In these types, because what we're usually looking at are molecular compounds, our covalent bonding, each line represents a covalent bond. We don't typically show our ionic bonds in this way. So this shows a shared electrons. And each line represents 2 electrons being shared between the molecules, between the atoms. So a single line is a single bond, and we're representing 2 shared electrons. A double line is what we call a double bond, and each line represents 2 shared electrons, so a double bond represents 4 total shared electrons. And a triple line, which we're not showing here, but that represents a triple bond, so that represents 6 shared electrons. So every line represents 2 electrons being shared. And of course the naming is fairly straightforward. Single, double. If we want to determine our empirical formula, if we're given a molecular formula, it's very straightforward. All we have to do is take our subscripts and divide them by the greatest common factor. The largest number that divides equally into all of the subscripts and gives us a whole number. If one of the numbers, one of the subscripts is 1, you're already at your empirical formula. You can't get any lower of a whole number than 1. So for example, C5H10O, we're going to go through this. So first off, an ionic compound that has 2 aluminum ions for every 3 oxide ions. So I'm just going to write that AlO3. So the question is, if I take my lowest common number, well, my lowest number is 2, but if I divide both by 2, I'm now going to get a whole number. So this is my lowest formula. Because if I divide 3 divided by 2, I'm no longer going to have a whole number. So this one's already empirical. However, if we look at this next example, C5H10O5, there is a number I can divide all 3 of those subscripts by, and I will get a whole number. And that number is, of course, 5. I can divide all of those numbers by 5, and I'll get CH2O. So that would be my empirical formula. If we look at this example, it might be hard for you to see the way it's drawn. So what you could always do is redraw it in the formula as opposed to our structural formula. So what we have is 1, 2, 3, 4 carbons. And we know that because they're represented as C. We have 2 nitrogens. And we have 1, 2, 3, 4, bless you, hydrogens. So our lowest common number we can divide everything by is 2. So what we get is C2H2N. So for this one, it's a little bit easier to rewrite it as this formula. Yep.
So since this is like covalent bond, does it matter the order? Like the 3 of them?
In general, no, not necessarily. If you wrote H2C2N, I wouldn't take off from that. When you get into organic chemistry, you're going to kind of know that carbons are typically bonded to hydrogen, so oftentimes you see CH and then some other atom. But the order for these are not necessarily any sort of order when we're talking about molecular compounds. I can even break this up. For example, oxalic acid, which we showed was that C2. Here, I would often see that broken up as C2 O4H2 because the hydrogens are associated with the oxygen. But that's not necessary. So with these, the order isn't really that important as you get more into molecular compounds in organic chemistry. You learn a bit more about that. But really what you learn is you won't be using formulas very often. You're going to be drawing it in these structures. And then organic chemistry, we don't draw carbons and hydrogens. So you're going to kind of learn a whole new terminology there as well for how we represent molecules. So the short answer to that is no, it's not necessary what order they're in. As an organic chemist, it's common that I draw carbon, hydrogen, then some other atom, but that's not necessary. I could put into C2H4, and that's still the same thing, into C4H4. So the order isn't that necessary with these. Now it is necessary for ionic compounds. Ionic compounds, we always draw the cation and the anion. But molecular compounds, not as important. And this one, this is another type of representation. We call this a ball and stick model because it's shown as balls and sticks. And it shows the shape representation. And oftentimes in the ball and stick models, carbons are drawn as a large black sphere. Hydrogens are drawn as a small white sphere, and oxygens are drawn as a small red sphere. If I gave you one like this, I would give you the key, but that's often how they're drawn. So this is actually C2. Then we have 1, 2, 3, 4, 5, 6 hydrogens and 2 oxygens. And again, if I gave you one like this, I would give you the key for reading that. But what we see is we have 2 carbons, 6 hydrogens, and 2 oxygens. But as you can see the geometry a bit more. It shows the 3D structure where this oxygen's coming towards you, this hydrogen's going back. This structure also doesn't necessarily show single or double bonds. I know that this is a double bond and this is a single bond, but that's because I know the bonding patterns of oxygen. You wouldn't know that from looking at this model until you know more. And you'll know more by the end of this class. So right now, you wouldn't be expected to know how these are necessarily bonded from this model. But of course, our empirical formula, we can divide everything by 2. Oops. And get CH3O. And again, the order of that isn't necessary. So this is our ball and stick models. And again, our ball and stick models represent the attachments, how they're attached, the order our molecules are attached, and they also give us a little bit of information about geometry, sometimes in 3D. This one is sort of showing a double bond, but oftentimes it won't, and we need to use our knowledge of how oxygen bonds to understand that it's a double bond, which you cannot do right now, and that's okay. Well, some of you might be able to do it, but most of you probably can't, and we'll work towards that later on in chapter 7 and 8 and 9. There's also this space filling model, and this is to represent the electron clouds of atoms that are being shared. So it looks like it's giving you less information, but it's giving you a little bit more. Like I said, no model's perfect. So the ball and stick, I like looking at better. So you sometimes see some of these models. And again, if I give you one like this, I'll give you the key for what the different colors mean. But typically carbon's black, hydrogen's white, and oxygen's red. Sometimes nitrogen is blue, but not all the time. So you don't need to memorize that. So for example, acetylene, our molecular formula is C2H2. Our empirical formula is CH. And this is one of those space-filling models that show how it is bonded. Benzene is C6H6. Its empirical formula is CH, which clearly doesn't tell you everything about it. You don't need to memorize these. I'm just showing you these different representations. Glucose, which is one of our sugars, is C6H12O6, but our empirical formula is CH2O. Now, typically, our ionic compounds are always represented in their empirical formula. So usually it's just molecular compounds that we have a big difference between our molecular formula and our empirical formula. So those covalent bonds. Molecular formulas, I just said that the order didn't matter for the way that you put in your atoms, as long as your subscripts were associated with the correct atom. That is true, but this compound, there is an exception. And that exception is, this is not a molecular formula. That's an actual ionic formula. So the fact that 4 of the hydrogens are associated with nitrogen, whereas these 3 hydrogens are associated with our C2 and O2 are very specific. And that's because This is a molecule made up of these ions and these ions that are come together to a 1-to-1 ratio. How do you recognize that? Well, we're going to talk about polyatomic ions and when to recognize them. I'm going to give you a list of some that you need to know. Though there are more in organic chemistry, but we're going to talk about the most common ones that we see. Now I can write this formula as C3H3C3H3O6 as still the total thing. But this one, because it's not an overall molecular formula, it does have some shared bonds, but it also has ionic bonds. So we're going to be looking at that. We're also going to talk about naming, because naming is going to help us to understand what our molecules are made up of. Now we're not really going to talk about naming organic compounds in this class. We're not going to get there. We're not going to learn how to name those molecular compounds, with the exception of really, really simple molecular nonmetals. But we're mostly not going to be talking about naming as in organic chemistry. And when you take organic chemistry, you're going to learn that naming system. It's going to be pretty much 2 semesters, and you're going to learn naming in almost every chapter when you talk about different functional groups. But we're going to talk about simple naming of ionic metals and nonmetals, and naming our acids, and naming our molecular nonmetals, our really, really small covalently bonded compounds. So ionic compounds are, again, compounds that are our metals and nonmetals, or a bond between 2 charged atoms or groups of atoms, which is where our polyatomic ions are going to come in. So metal atoms form cations and nonmetal atoms form anions, and we've discussed this already, so I'm just reminding you. Oftentimes, our ionic compounds don't exist as a molecular unit like our molecular compounds exist. So a molecule of acetic acid always looks like acetic acid, and it's associated with itself. A molecule of sugar is always associated with this formula. If I were to dissolve a molecule of sugar, the molecule doesn't break apart in the dissolving process. It just gets surrounded by water. But in ionic compounds, they exist from the attraction between our cation and our anion. And if we actually take salt and dissolve it in water, we're breaking apart that interaction between our sodium and our chloride. And that's not the same for molecular compounds. For molecular compounds, we're not breaking any of our covalent bonds when we dissolve. And we'll talk about solutions chemistry in more detail later on in this class. But they exist as an array. Oftentimes, they exist as crystal structures. So you often hear that. So what we do when we represent the formula of ionic compounds is we always represent the empirical formula, the lowest ratio, whole number ratio between our atoms. So this is just representing that if this is salt, sodium chloride, it doesn't just exist as one sodium and one chloride together, but exists as an array of sodium chloride, but always in a 1-to-1 ratio. And that's how that exists in its solid form. Compounds of metals and nonmetals are made of ions, and oftentimes they might contain polyatomic ions. So we do need to talk about our polyatomic ions. You need to know these and know the names, because you're going to need to know them for naming. I won't have you memorize much in this class. I will have you memorize this. I will not give you this. I might give you this for a quiz, but I won't give you this for the exam. So I really recommend you knowing it. Don't bank I'll give it to you for a quiz. These are some of the most common, so these are the ones you need to know. I'm not saying that there's not others out there. We will learn in organic chemistry you can form a formal charge, and then it's always going to form an ionic bond with the counterion. But these are our most common ones and the ones you need to know. Notice there's only one overall positive charge polyatomic ion on this chart, and that's the ammonium ion, NH4+. Not to be confused with liquid ammonia, which is NH3 and has no charge. So NH4+ is our only positively charged one. Our other ones are all overall negative, though some might be overall -1, whereas some are overall -2. this charge is associated with the whole group of atoms, not specifically with one atom. When you get into organic chemistry, you'll learn it is specifically associated with one atom, but for now you're not doing that. So you're just looking at it as being associated with the whole ion. Notice that we have several atoms attached through covalent bonds, but it has an overall charge. So all of these are nonmetals, but they overall have a formal charge, so they're not overall neutral. And because they overall have a charge, they're going to ionically bond with something that has an opposite charge. And with the exception of NH4+, these things are going to bond with metals. Now, NH4+ could technically bond with any of these, which is how you can have an ionic bond with no metals present, like the example that I showed on the eye clicker question that we'll revisit. But otherwise, everything has a negative charge, so they're all going to bond with metals. And that's their attraction. So you do need to know these. So looking at this one is actually a covalent bond between our NH4+ here and our C2H3O2 minus. Where'd it go? Which is here, our acetate ion, which is just the ion of acetic acid, and acetic acid is vinegar. So when vinegar is mixed with water, it can form this. And that's why it is not an overall molecular compound, that example. So you do need to know these, and we'll talk a bit more about them when we talk about naming in a couple of slides. So I won't have you memorize much, but you need to know all of those on that table. Now, one thing to note, a cation won't form unless if something can take its electron. So that means that a cation and an anion are going to form together, because one can't form without the other. If something gives up its electron, something else has to take the electrons. So when metals and nonmetals combine, electrons are transferred between the atoms. And ion formation is shown here. So here we have this metal. This metal gives up its electron to form a +1. So this metal is represented likely as a metal in the first row of periodic table. There could be a transition metal. It's just metal, just in general. Whereas that nonmetal had to accept that electron, which you can see here in red, forming our ionic bond, which is just our attraction between our positive charge and our negative charge. Now, our compounds typically are neutral. They have no charge. So to determine our ratio of how many metals are going to interact with the amount of nonmetals, we just have to balance our charges to get a net charge of 0. So for example, if sodium plus combines with S2 negative, sulfur 2 minus, and remember, I could figure out what those charges are based on the periodic table, because our sodium forms a +1 cation, and our sulfur forms a 2 minus anion. How many sodium to sulfur ions are going to interact with each other? Well, again, we have an overall neutral charge, so that means that we're going to need 2 sodium ions for every 1 sulfur ion, because we have a charge of 2 minus for sulfur. And when we draw that as an ionic bond, we're going to draw that as N2S. So notice, if I take this 2, that means I have 2 positive 1 ions. So 2 times +1 is going to be +2. And then I can cancel that out with my -2 for my 1 sulfur. So they need to balance each other. And this is our empirical formula, because there's no other number we can divide this and get a lower number ratio. So our charge of our ion is dependent from the element's position on our periodic table when we're talking about our main group elements, which we've talked about before. So if you know that, then you can figure out your formula for your ionic compounds. Now our polyatomic ions, you need to know those charges because that tells you how many polyatomic ions will associate with the metals. So for our main group elements, remember, 1, 2, and 3, our cation charge equals our group number. For our nonmetals, our charge equals our group number minus H. This isn't new. I showed you this a couple of weeks, like last week we talked about this. So then we just need to balance our charges. So for the first one, let's say we're doing aluminum ions and oxide ions, and we want to know our formula. Well, our first thing is we can write our symbol for our metal cation and its charge. And in this case, our metal is aluminum. So it's Al. And Al is in the third 3/8, so it's going to form a 3+. Then we want to write our symbol of our non-metal, bless you, which is oxide, which is our oxygen. And oxygen is in 6A, so it'll have a 2-. So now, what we can do is we want to cancel out and have it in a neutral overall compound. So our charges, when added together, equal 0. So what we can do without the sign, because of course we can't have this just tells us our amount. We can do what's called the cross method, where we take the charge of aluminum and cross it down to that's the amount of oxygens we have, and we can take the charge of oxygen and cross that down to get Al2O3. This is just a simple method. You can always check this because if you add your charges, you should get a total charge of 0. So you can double check. Why does this work? Because all we're doing is balancing our charge. We have aluminum as a +3, oxygen as a 2-. If we had a 1-to-1 ratio, we have an overall +1 charge. We don't, so we're just balancing it. So we can double check that. If we have 2 aluminums with a +3 charge, plus 3 oxygens with a -2 charge, if we add that together, we should have a total overall 0 net charge. So that'll be +6 plus -6, which is 0. Now, if this isn't the empirical formula, you should write it as the empirical formula. There won't be a lot of cases where that can happen, but there might be. So, for example, if I divide both of these by 2, I won't get a whole number, so this is my empirical formula. But if I came across one where I had another empirical formula, that's what I want to report. You always report your empirical formula with your ionic compounds. So looking at potassium ion with our nitride ion, potassium is in dead group 1A, so it's plus. Nitrogen is 3-, so we want to balance that. This one's pretty straightforward. We'll need 3 potassiums to balance every 1 nitrogen. So K3N. And notice when we write our full molecular formula, we don't no longer show the charge. The charge isn't changing. That charge is associated with the periodic table. Calcium ion is our 2+, and our bromide ion is 1-. So, bless you. This one's fairly straightforward as well. We need 2 bromine ions to balance with every 1 calcium for that charge to cancel out. So CaBr2. Again, notice if we only have 1, we don't show the 1 in our formula. Now our aluminum ion and our sulfide ion, we have our Al3. Oh, we just went through that one. So that's a repeat. We just went through it. So you can use the cross method, or you can rationalize how many aluminums you need to balance out how many sulfurs. So we need 2 aluminums for 3 sulfur atoms for them to balance. And you can always double check to make sure that your total charge equals 0. Now, as far as naming, there's going to be some nicknames. You learn them by experience. I'm not going to have you memorize them. For example, baking soda, which is how you know it, is NaHCO3. I know it as sodium bicarbonate instead of calling it baking soda. Table salt is NaCl. So that's not our systematic name. That's not our chemistry name. And sometimes common names are used for molecules, but there's always a systematic name. So we're going to talk about systematically naming our ionic compounds. So our systematic name is fairly simple. The name is simply named by our ions. If it's a cation, it's just a metal name. Fairly easy. So the calcium is just calcium. We're going to put calcium. If there's a variable charge, one of our transition metals that are not in our main groups, then we do need to specify the charge, and that charge goes in parentheses, and we use Roman numerals. And it's very important because if I don't specify in my name whether I have copper 2 or copper 3, then I can't write my formula because it could be in those charges. So if it is a transition metal, you must show the charge. But any of our invariant charges, our main group metals, don't need that. So it's just a metal name and in parentheses the charge. Polyatomic ions, it's just the name of the polyatomic ion, which is why you need to know the name as well as what charge it has and what it looks like, what atoms are in it, what's the ratio. So you need to know that. If it's an anion, then the nonmetal is the stem of the nonmetal name, but instead of whatever the last 3 letters are, we change it to IDE. Kind of like we did when we named our ion. So if you remember our sulfur, when it's an ion, we call it the sulfide ion. So when we were talking about our bond and our ionic compound, we just drop ion, but we use sulfide. So the end is IDE. With the exception of our polyatomic ions, because then it's just the name of the polyatomic ion. So whatever that name is in the table, that's what it is. We're not changing it at all. But any of our other ones, it's just going to be the nonmetal name plus I. So let's look at some examples. And again, it's very important that if we have invariant charges, any of our transition metals, that we show the charge in parentheses. That if they are, and you don't even know this table, this is just some of those invariant charges. But notice the name doesn't change. And if you recall, when we talked about naming cations, we just named it the metal name plus cation. So that's all we're doing with the name. But our metals that have variable charges, we need to specify. So if you notice, chromium has a 2 plus or a 3 plus, we need to specify that with our parentheses. 10 has a 2 plus or a 4 plus, we need to specify that with our parentheses. Mercury can have H2 2 plus or Hg2 plus. And we represent that actually by Mercury 1 and Mercury 2. Now there are older names, and these are our common names. For example, the Fe comes from the fact that iron used to be called ferric and ferrous. That's why it's Fe and not, named after iron. There's a couple of other ones. Copper is Cu. It used to be called cuprous or cupric, depending on which charge. That's where the Cu comes from. You don't necessarily need to know those names, but it explains where the symbols from the periodic table come from. But we're going to be using the systematic name, which is this. How do we determine the charge? Well, if we're given the name, we know the charge. If we're given the formula, we can determine it because we'll know the charge of our nonmetal portion. So if we know the charge of that, we can figure out what charge our variant compound is. Which is why it's really important in the name that we specify what charge we have. So when we're naming these, all we have to do is determine the charge from the position on the periodic table, name our anion, and change the naming to I. So carbide, silicide, phosphide, nitride. As you can see, it's all just changed in name to I. And then we just put that together. So you name your metal first and your nonmetal anion second with our ionic compounds. So let's look at this one. We have CSF. And our cation and our anion, we have CS. It's in group 1A, so we know it's CS plus. And our fluorine, we know is F negative. So when we identify that together to name it, it's just going to be cesium and fluoride. So we just put that together as cesium fluoride. We don't need to show anything in parentheses because we don't have it in a variable charge. It's only going to be a +1 because it's in group 1A. So you always want to double check to make sure your metal is in a main group. Otherwise, you have to show that charge. If we look at this one, we have potassium and chlorine. Potassium is a main group element, so it's potassium chloride. Magnesium and bromine. Magnesium is a main group element, so it's magnesium bromide. Aluminum and sulfur. Again, aluminum is a main group element, so it is aluminum sulfide. You should be able to read a name and draw the compound in the right empirical formula. You should be able to take the compound and draw the name. You should be able to do both. As far as our variable charges, the only difference is we need to specify the charge in parentheses, which means we might have to calculate the charge. So for example, we have titanium chloride. We know we have 4 chlorines, and each fluorine has a -1 charge. So if we only have 1 titanium, we must have a 4+ charge. Because remember, our overall charge is 0. You can set this up, if you'd like, as a algebra. We don't know the charge of this. We know our charge of chlorine. So we know that 1 times x, because we only have 1 titanium, plus 4 times our -1 is going to be equal to what? What's going to be our overall charge? 0. So you can calculate what x is going to be. And remember, your metal is always going to be a positive. So we can calculate that as +4. So now we just put that together. Titanium, 4, chloride. If we look at chromium, again, we know oxygen has a 2- charge. So we can calculate what chromium's charge is. So we have 3 oxygens, and each oxygen has a 2- charge. We only have 1 chromium. Again, you can set this up as an algebra equation. You don't have to. That's the way I like to think about it. And overall, our charge should be 0. So for that to balance out, our chromium must be a 6+. Again, our metals are always going to be positive. Periodic table. How do you know your charge of your nonmetals? It's in group 6. It's in group 6, so it has a -2 charge. You should know how to do that. And if you know how to do that, then you know your charge of your nonmetals. As far as iron and nitrogen, nitrogen has a 3- charge. We have 2 of them. Now we have 3 irons. We don't know how many we have. And again, we know what nitrogen's charge is based on where it is on the periodic table. Well, you can, but if it's in the empirical formula, you might be incorrect. So, for example, CuO. You know the charge is 2-, so then this must be +2. But if you just did the crossing, you might say it's +1. So to avoid that, in general, the crossing could kind of work. But sometimes it might not. If, like for example, if I did the cross of this, but the empirical formula is CuO. So you gotta kind of watch the cross method. You can't go wrong by doing what I'm doing here. So here when we solve for X, we see that our iron must have a +2 charge. So this would be iron 2 nitride. So if we look at this example, again, here we're looking at gold. You don't need to know which charges gold forms, but you do know which charge sulfur forms. So our charge in our anion, sulfur, is 2-, based on where it is in the periodic table. So we can then calculate our charge for gold because we know we have 3 sulfurs. And our total negative charge is 6-, and we have to balance that. So since our total positive charge is going to be +6, we know that we have a 3+ charge on gold. Again, you can set that up as an algebra equation as well, which is what I was doing on the examples before. So as far as naming it, it would be gold 3 sulfide. Now if we are writing the empirical formula from the name tells us the charge. So then we're just doing exactly like what we were doing before. We know we have manganese 4, and we know what our sulfide ion looks like. So Mn4+, and our S2-. We can do the cross method for this. We will get Mn2S4. However, this isn't our lowest number ratio, so we want to write the empirical formula, which is MnS2. Which again, here's a case where the reverse of the cross would give you the wrong charge, unless if you know what you're. So that's why the algebra formula is a little bit more clear. It's very, and you can always double check to make sure that your overall charge equals 0, which it does here if we do double check. Remember, your metal is always a positive charge, so if you come out with a negative charge, you did something wrong. There's a lot of ways you can check yourself when you're doing these to make sure you don't make a simple mistake. But you absolutely have to draw the number in parentheses. If you just put manganese sulfide, I have no clue how to balance that because I do not know which charge manganese atom you have. So that has to be specified in the name. Now this example, notice, you know the charge of copper, but this is copper 2 nitrate, not nitron. So this is not either C or D, because nitrate is not nitrogen. Nitrate is one of our polyatomic ions. So you need to know your polyatomic ions. Again, here's our polyatomic ions that you need to know. And notice, nitrate is one of them. And it's NO3-. So when we are drawing our formula for an atom that contains a polyatomic ion, if we just have one of those polyatomic ions to balance the equation, that's easy, that's simple. But if we have multiple, then we have to put the entire polyatomic ion in parentheses before we put the subscript. Because what this tells me is, for Cr2O7, I have a total -2 charge for this whole thing. We cannot break up Cr2O7. That entire group of atoms has a 2- charge. So if I'm balancing that with something like aluminum, which has a 3+ charge, I'm going to have multiple of those ions, and I have to specify that by putting them in parentheses. So oftentimes, again, we'll have those identified in the formula. You have to know your name and your charge and what the polyatomic ions look like because that's how they're specified in the name. If I tell you I have ammonium acetate, you know that the formula is NH4C2H3O2. And you need to know that by memorizing this table. Always, again, name your cation first, your anion second. And in most cases, your cation is going to be in the middle, with the exception of if ammonia is your anion. Then if ammonia is your cation, you name that first. But overall, most of these are negative. So these are usually reacting with metals. So just a little bit to help you kind of memorize the table. You don't need to memorize these slides, but these patterns might help you to memorize the table. First off, elements in the same column form similar polyatomic ions. So you'll see similar polyatomic ions on that list. For example, chlorine and bromine both can bond with oxygen, with 3 oxygens to form an overall -1 charge. And you see that in the name, they're both named very similar, they both look similar. And chlorine and bromine are in the same 6A. So we have our chlorate and our bromine. 7A. I don't know why I said 6A. If the polyatomic ion starts with an H, oftentimes hydrogen is added before, and then a +1 is added to the charge. So for example, carbonate, when there's a hydrogen in front of it, it's hydrogen carbonate. And notice the difference in the charge, 2 minus and 1 minus. 2 minus plus 1 would be 1 minus. Again, you don't need to memorize this. This just might help you with learning the table.
Is hydrogen carbonate an acid?
No. It's a base. Because overall it has a negative charge. It doesn't want to give up its hydrogen. So here's some of the 8s. Notice that the 8s usually start off there. And then 8 ion plus another oxygen is going to have the same charge, but per will be added in front of it. So for example, chlorate has 3 oxygens, but ClO4 is perchlorate. So the per is just added in front of it. 8 ions minus an oxygen has the same charge, but ite is again. So ClO3 minus 1 is chlorate, ClO2 minus 1 is chlorite. And you'll see that with the carbonate ions as well, with the borate. So you see that those kinds of trends when you look at it. Again, this just might help you memorize the table and kind of cut it down. You don't have to memorize them by following these trends, but it might help you to better memorize them and remember them. And again, when there's an 8 ion with 2 oxygens, usually you'll see the hypo prefix and then the ite suffix. So hypochlorite. And if you compare that to our table, you'll see that, for example, phosphate, PO4 3-, you had a hydrogen, it's hydrogen phosphate, and notice we had a +1. So PO4 2-. The perchlorate and permanganate, you'll see some of these trends, hypochlorite, chlorite, and chlorate. You'll see it also for sulfate and hydrogen sulfate. So it'll kind of help you memorize them. Nitrite and nitrate. But you don't have to necessarily memorize those trends I just went through. Why did my alarm go off? Oh, because I still have 2 more minutes. So if we're looking at an example like this, if I'm naming them, sodium, pretty straightforward. My cation is going to be sodium. But I need to recognize my polyatomic ion, which is SO4. Now I know it's SO4 2- because I have 2 sodiums, and each sodium has +1. So you might need to know that to know the charge. So my polyatomic ion is SO4 2-, which is our sulfate. Sulfide is SO3 2-. So it's our sulfate. So our name is just sodium sulfate. And we don't, now if this is with our metal that is not a main group metal, we still need to put the number of charge in parentheses. So let's say we were bonded with copper, we need to know that charge of copper. So work on this one, and we will continue this lecture on Wednesday. My watch time is off. Ah, here it is.